Hey, I want to talk to you today about an app on Splunk base that really goes through how machine learning can be, explored, created, and operationalized on Splunk. It gives you that complete end-to-end example. So this is on Splunk base. We have a number of apps on Splunk base, including the machine learning toolkit, which is a critical component for this app. The app we're going to talk about today is the DGA app. It's the DGA, Domain Generated Analysis app on Splunk. So the idea is that you have some set of attacks that are happening on your DNS. You're interested in detecting what sort of attacks are coming in, what sort of DNS requests are authentic or legitimate, and which ones are coming from different attacks, right? So we're going to use machine learning to detect the problem, to build a model to describe how to detect it. We're going to put that model into production, and this is a great example app for you to download and use as just an example of how machine learning can be applied to really any problem. So if we go over to my local copy of Splunk, you see I have a number of apps installed. One of them is the DGA app for Splunk. I'm going to load it up. When you download it for the first time, you're going to have this little button down here called Setup. I really recommend you go to Setup and follow the instructions for turning on the data system. We have a number of different dependencies you're going to need to download. These are other apps from Splunk base, other things that we're using inside of this workflow. There's a lot of settings and steps here to go through so that you have your input data created locally. That's a sample set of data that we publish. We also want to make sure that you go through the steps and have the different machine learning models created and have a piece of interesting little SPL that creates net new events on an index for you so that you can see how machine learning can be applied to net new events as they're flowing through that demo. All right. So this is a good page to start with. Go ahead and go through the setup steps. There is one that takes a rather long period of time, step 10. That does take 2 to 3 hours. It's going to be generating a bunch of things in the background so that we can see this walkthrough. So the app itself goes through the 5 steps of machine learning. We have the idea of exploring some data that's related to a problem we're trying to solve, trying to identify if machine learning is going to be a good target for it. We're going to enrich the data that we've identified in our data analysis, enrich it so that the features, so that the fields, the contributing values to our machine learning models are have the most amount of information that we can gather. We're going to create a bunch of machine learning models in this case, so that we can see which algorithm is best suited for this particular problem, or maybe make an ensemble of all of them, right? Make them vote. And then finally, we're going to tie that machine learning to real-time data in Splunk and sort of see how you would build a tool to monitor and act on the machine learning itself. And we might get to testing and benchmarking when we talk about comparing the models we've built to a data set that's, say, 34 times bigger, and just seeing if we didn't update the models onto that data, if we just pretended that the models couldn't be retrained, then we could actually see what that would look like on a much larger data set, see where our errors might be and how we could improve the system. So let's walk through this. Let's walk through the process that really you're going to go through for any machine learning build out in Splunk. So number 1, exploratory data analysis. So when we talk about exploring the data for a particular problem, in this case we're looking at DNS, and I've got a small set of labeled data, about 200,000 events, where I have got a label, a ground truth that's telling me that this particular domain is a legitimate domain. It comes from a legitimate source, right? On the other hand, I have a whole bunch of other classes in here. I've got the idea of illegitimate ones that come from domain-generated automated attacks, right? These attacks like China AD or WannaCry, they generate DNS strings synthetically inside of their attack. And we are going to try to identify those with machine learning in an automatic way. So here's some labeled data. This is a known DGA, known way of generating domain names, like this one right here that is actually incorrect. We can see that it's even from a subclass, because we have this set of data that tells us which specific type of domain-generated attack is it coming from, right? So we've got 2 pieces that we're trying to solve. Can I detect if a DNS request came from a particular attack algorithm? And can I tell if it's which subclass it came from, right? So I could monitor to see if my attacks are coming from a new subclass, are they coming from a class that I've seen before, etc. So this is just kind of exploring the data. We can see how the different domains are separated across our data set. We can kind of look at the different pieces of information. This is all kind of a visual inspection to sort of give us the idea of what is the data we're looking at. Let's see if we can explore that. But let's use a few pieces from the machine learning toolkit to immediately analyze and mine that space so that we can mentally understand if we have a good separation in our data. If we can draw a line between the points, or a circle or a square or some sort of shape, if we can draw a line through these points and separate the different colors, then we're pretty sure that machine learning can solve this problem. Not sure what type yet, not sure if we have all the data yet, we're just exploring. So if we look at this carefully, it says we're doing an n-gram analysis, 2 to 3 character groups of the domain name with PCA k=3 by class. That's a bunch of text explaining to you the steps from the machine learning toolkit, right? So we're doing a text mining approach known as text frequency inverse document frequency, which is part of the machine learning toolkit, TF-IDF. It's an algorithm that takes a string like this and allows you to say, hey, I want to see the frequency of every 2 to 3 character groups, and I want to have it inversely weighted to tell me how rare it is across the entirety of my data set. Right? So it's going to create a whole bunch of numeric values. In this case, it's going to create 100 to 200 net new numeric values for all the different combinations of characters that it finds, which is a really large dimensional space, right? If you can graph or visualize 200 dimensions, give me a call. That's a seriously amazing thing to be able to do. We should probably talk about monetizing that somehow, right? But the reality is that we want to be able to draw these things. We want to be able to visualize the space we just created with text mining. So we use another app on Splunk base called the 3D scatter plot, which is already baked in here. And it gives us the ability to kind of look at the different separations, right? The separation in the data that came out of text mining, the separation. And we see that the yellow and blue, that's, if we look carefully, that's class legit is blue, and the yellow class is DGA, that's the attack ones. We can see that there's a pretty good separation. Not an amazing separation, like there's some clear overlap here as we zoom in and look at it. We can see some overlap is occurring in different sets of this dimension. But there's a good separation. We probably can create a mathematical model or a series of models that describe the blue dots as opposed to the yellow dots, describe the legitimate DNS requests versus the illegitimate DNS requests. And if we look at the subclasses, right, so in this case it looks very similar, right? The blue all looks the same, but now I have these multiple colors replacing these giant yellow swashes. Now what I've done is I've just selected the different classes, so I can see that this is DGA Lockley, right? So Locky is really highly concentrated on this dimension set, right? And there's a couple of them sort of spray aside, but really this is the primary attack from it. If I look at the purple's in 3 different directions, but it's always on the exterior, right? It's on the exterior of groups. I can kind of see that even the subclasses are separating easily. Now you may be thinking right about now, hey, I thought I could use machine learning in Splunk for any use case. You can. We're doing a walkthrough here of security because it's a well understood problem in this case, right, DNS, and we're trying to highlight the steps you can take to solve any problem, right? So this is data exploration for a single string, a single value going through time that we're going to slice into characters and talk about their inverse frequency and try to detect a DNS. Maybe for time series, you might build out a different series of graphics here or a different series of steps, but you're still going to start with, what is my data? Explore your data. So I'm going to go back to the dashboard so we can go to step 2. Okay, so step 2, feature engineering and selection. So we just created 3 dimensions of text inverse frequency document scoring of character n-grams, right? We've created that. That's these PC1, PC2, PC3. That's all coming from the principal component analysis second step in the toolkit. All of that is taught in the Splunk for Data Science class, or if you just go onto scikit-learn or any of these other places out there on the internet that teach data science step by step, they'll talk through how you get those other pieces. But we still have that data in Splunk, right? And we have a bunch of other things in Splunk. So for example, we have something called the URL Toolbox app, which comes with a bunch of interesting features. And one of the things it comes with is the ability to enrich a string with things like the consonant ratio, right? So if I look at this ratio, this domain over here, I'm looking at the ratio of consonants to the rest of the characters in that string. I'm looking at the digit ratio in that string, and the length, and the meaning. So in other words, how much like an English word, how many English words are in there. And what is the Shannon entropy of that string, and what is the val ratio of that string. I'm getting all of that by just adding another app in Splunk and putting it into my workflow. So I'm enriching my space, I'm creating new features. All I'm doing here at the top is starting with the data from the previous step, and I'm enriching it with an app from Splunk base or with a lookup from somewhere else or data from somewhere, right? We're enriching our space. And we want to kind of explore that. I know some of this looks like a bunch of weird art. I just kind of want to explain what we're trying to do here. We're trying to look at things like one of these dimensions, the Shannon entropy, right, along the bottom, and then along the side we're looking at the meaning ratio. So how much like a word is something based on, compared to the amount of entropy inherent in the string, right? So if we look at this, we're seeing all these different classes. We're seeing they separate really, really well, right? They separate really well. These two values are probably going to be extremely useful to us. And if we go over here to the right, what we see is that, you know what? We can actually analyze all these fields along the top and use something called the analyze fields command, or the field selector command in algorithm, I should say, in the toolkit, to tell us which of these values, which of these has the greatest balanced or singular accuracy contribution to what we're trying to do, right? Which, should we use all of these? Should we use some of these? This is telling us in a weighted way which are the best ones. And if we look carefully, we see that Shannon, right, and meaning are quite high up. We see that PC1, PC2, PC3 from text mining are definitely up there. Val ratio is very important, but domain length is not as important, right? It's got the least amount of accuracy. So that's all coming from, again, sort of the analysis of this step. I want to feature, engineer, and then I've got to select. I want to reduce the number of things I'm going to feed into my model. Now, in a visual way, I still want to inspect this. Maybe I don't fully believe the analyzed fields. Maybe I want to look at this and be able to look at it in as many dimensions as I can on a flattened plane. So that's what parallel coordinates comes in as a really great way to view that. So this is another app from Splunk base. It's a visualization. If I look at this carefully, I can come in here and look at, say, the top values from the meaning ratio, and I can see that for the most part, the legitimate class goes through each of the dimensions, passes through more or less this space, and comes out legitimate. But some of the DGA attacks are still coming through, right? So still coming through. So while this is going to be a great variable, great contribution, great feature for my models to learn on, I need other dimensions to help refine this and make this path from some data set, right, coming through and correctly predicting all the way on the right. So that's kind of the separation of the data. It's for visual exploration. So we've done step 1 and step 2. Let's go to step 3. So when I look at step 3 is about creating the machine learning models on the data we explored and enriched with features. So we're going to open that up. I like to say, why make one model when you can make 4? So in Splunk, using the machine learning toolkit, we can make as many models as we want. We can use algorithms that come out of the box, with the toolkit, or we can go out into the wide world and wrap really any algorithm that's in scikit-learn, SciPy, StatsModel, the really popular Python for scientific computing space. Or we can even go in and use the ML API as part of the toolkit to bring in our own analytics. So, if you're reading a research paper or a thought article comes out describing a different way of analyzing this data, a different way of selecting different models or adding net new features, you can bring those in through the toolkit. You can bring those in through SPL, however you want. But we're going to train 4 models. We're going to train a random forest classifier, a support vector machine, a decision tree classifier, and a logistic regression model. We're going to build those all, and we're going to get a quick scoring of them from a confusion matrix that's part of the ML toolkit. And it's going to tell us things like, if given the ground truth that we know this came from an attack of DGA, we correctly predicted it 24,890 times and incorrectly predicted it, saying that it was legitimate 175. So it's giving us a good number to tell us how these things score against each other. But we're going to evaluate them one step further. We're going to say, I can graph all these numbers from the top. I can graph them all together, and I can clearly see that while random forest has the best value in terms of correctly predicting legitimate, right? That's that first color bar, and I can see that my incorrect values are starting to increase. What I'm really looking at is the false positives. How often am I making false predictions? So let's just refine that graph one step further. Let's just view the failed predictions over here on the right. Now we can clearly see that random forest is the better selection. Maybe I might be reading a research paper and it says, hey, why don't you make these things vote or combine them in different ways? You absolutely can. All of these models are available in SPL, right? You can just combine them together and have them vote. You can do whatever you want with these model outputs. But that's kind of a great question. Like, what do we do? I mean, we've gathered our data and explored it. We've created meaningful features and selected them. We've built 4 machine learning models, but we haven't tied them to an action yet. And it's actually pretty simple to tie it to an action. That's why we're going to go over to that panel 4 next and look at what that looks like. So panel 4, we're operationalizing machine learning. We're taking the machine learning that we have created in step 3. We're taking all that knowledge that we gathered and created to power the machine learning, and we're tying it to real-time data so we can take action. We're getting value from the machine learning by tying it to real-time data and taking an action. So this is an example dashboard. Here at the top, I could select any one of the algorithms that we used before because that's how we built it. We can go into the time range and we can talk about what time range do we want to do. In this case, I'm doing it on real-time data. I'm doing it on real-time data as part of your setup process that generates some random incoming new data so that we can test it and show what this might look like. So we can count the number of predictions as we're going through. We can look at the trend of true predictions and false predictions. Think about a machine learning model as just another service in your ecosystem. You need to monitor it. You need to monitor the data coming into it. You need to take action based on if it's a healthy model, right? If the data coming in, if someone changes the inputs, then the model wouldn't be valid, and you want to be able to alert on that. If your intern comes in and rewires your DNS router or changes it in some way, or even just like flatlines it to Splunk, you want to be able to take action and alert on that. So this is just like any other service in Splunk. You're monitoring it, you're analyzing it, you're applying machine learning and taking action. We can see the performance over time as it sort of moves through and whether it predicted true or false. We even can see the results, right, of what the data was versus my predicted class. And finally, we can actually give a human, like an expert, like a security analyst, we can give them the ability to feed back into the model. So we can give the user a legitimate and illegitimate button here. I'll just click legitimate to sort of prove the point. Now, the next time the model retrains, the next time the model on its training cycle analyzes net new data, it's going to be told that the expert said that this was a valid string. This was a valid domain. So instead of thinking of it as an illegitimate domain, it's going to relearn the information, but it's going to process this now as saying that the user was correct. This is just a workflow in Splunk. You can use this concept in any machine learning model, any custom machine learning model in Splunk. You can add the ability for a human or a series of humans to vote and give back information to the model. You can put the human back in the loop, right? That's the idea. And what does this look like when we talk about putting it into production? So this is a great walkthrough of kind of talking about the automation part, the automation of the ML classification, but still allowing for manual adjustment and refinement, as well as automated action based on the blacklist and whitelist for domain-generated attacks, DNS attacks. The same workflow can be liberated and used for really anything. I mean, if you really abstract what we've gone through here, we've gone through the first 4 steps that you're going to basically put into production for almost any machine learning use case. This is just a really great example of a thing you can pick up, install in your system, and really understand it step by step. How do I build a machine learning model? How do I get value out of it in Splunk? Now we still have the 5th step to go through. The 5th step is where we're going to compare what we've already built today. We're going to compare it to a much, much larger data set without allowing the models to adjust, right? So one of the things we do with the machine learning toolkit is we have models that we create and we tie them to scheduled retrainings, or we tie them to an action button where an operator can tell the machine learning model to retrain itself, relearn over net new data. There's automation versus manual, whichever one you want to do. We're not doing that today. We're just taking a data set much, much bigger and using the models we already have. We're going to see how accurate they were across that whole space. So I'm going to scroll back up to the top. I'm going to go back to the main page. So over here on the last step, we're finally at testing and benchmarking. So we're going to take a much, much, much larger data set. In this case, it's 34 times bigger and 10 times more DGA subclasses. So we started with 3 subclasses. I've now got a data set that's got a lot more data on it. Here's the domain data set also for WannaCry. We're going to see how this would have done. Again, without any more retraining, millions, a million plus events, right? So we can see that we didn't do a great job detecting some of these, like DNS charger. That's clearly a place that we could put in some more features, or more importantly, allow the model to train itself on that data set, train itself, and then it would be able to detect it better. And we can see that the accuracy of the model as we're going through, we're getting more and more accurate because we're getting towards the classes that we've already seen. We've seen these classes before, so new events in these classes we understand and correctly attribute. With some of these, where we see the green bars, we're only catching maybe 40%, 50%, 60% of those attacks as we get into net new types of attacks. Again, that's where retraining is so critical. Allowing the model to learn as new data comes in, allowing the model to learn off of human guidance, human intelligence, critical part to really making models bulletproof, right? So when we look at the domain names that came from WannaCry, remember that's an attack that didn't use those three things before: NuGauze, China ID, Lockly version 3, didn't use those. And we didn't know what the classes were. Those would have been net new domains that came in for WannaCry. We would have detected every single one with this model set. Even though we never had WannaCry in the data set, we are looking for in the training data set, because we have built that to correctly separate those points in step 1, right, the blue and yellow points. We've correctly separated them. We've built models that were enriched and with meaning ratio and Shannon entropy and all the other things. Because we built those models very carefully, we're still able to detect some of the net new attacks without retraining. So this is just a great example of still detecting an attack even though it wasn't part of the labeled data set you started with. So that's the idea. That's the idea. Step 1, step 2, step 3, step 4, step 5. That's the idea of building a machine learning model in Splunk, building the workflow that you need to support that machine learning model, and then tying that to some sort of real-time action, some type of human-in-the-loop intelligence, and getting value from it. I hope you had a good time listening.